So this is another type of way that you can kind of look at double integrals. So this is actually a little bit more close to home because I'm a statistician, so I really like this part. So when we think about double integrals over general regions, we can actually have this integrand be represented with probability. So just to give you guys a little bit of a gist of it, I'm not going to expect it to know a whole theory of probability, but that way you guys can see where this is all coming from. So we saw that if I wanted to take the double integral of a density function, what we end up getting is the mass. Okay, so we end up getting the mass of this particular object or surface. Now, if I know that this function itself is is a probability density function, okay, then we can actually find the probability. So let me kind of define a little bit of what a probability density function is. So a probability density function f means that if, let's say this is a continuous random variable. So basically all that just means is that one example of a continuous random variable would be weight. Okay, we know that not everyone has exactly the same weight or the same height. These two values are continuous. Someone can weigh 180 pounds, someone can weigh 123 pounds, someone can weigh 122.3 pounds. So we have various different weights. So let's say there's a function out there that describes the weight of every single San Diego person. Okay, so we know kind of like some sort of function, and this function basically tells me, hey, you know what, give me a weight. Give me a weight, and I'm going to plug in that particular value, and I will tell you what is the probability of you encountering someone who is around that weight. So if I wanted to find the probability that this randomly selected person weighs between, I don't know, 150 to 155 pounds, I can plug it into my probability density function, do a little bit of math, and it'll output a probability. So the input will be what the event that you want to occur, and then the output will be the probability. So whenever you want to integrate the whole function for all values of x, where x is the domain of this particular function, the integral will equal 1. Okay, so, and that kind of makes sense for probability, because probability can only be up to 1. This is a total probability. And just to give you guys a definition of probability, probability is the likelihood of an event occurring. So how likely is this for it to occur? So if I were to flip a coin, how likely is it that I will get heads? Well, it just will be 50-50, so 1/2. Okay, if I flip 2 coins, how likely is it that I'll get and I flipped 2 coins and maybe I flipped it 4 times, how likely is it that I'll get exactly 3 heads? That is another type of probability. So that's something that you can compute. So the probability that x lies between 2 different values is basically integrating f from a to b. So if I want to find the probability, this is just notation, fancy notation, probability that that random variable, maybe like weight or height, is between these 2 numbers is basically just integrating a to b of this function. Okay, this is a single variable case. So we're assuming that x is a random variable that only represents one particular event. So maybe like height. Now let's say you had 2 different random variables, so maybe height and weight. If I have this height and weight, what is the probability that the height will be between these 2 variables, these 2 numbers, and the weight will be between these 2 variables, these 2 numbers? If my weight is between these 2 numbers and my height is between these 2 numbers, what is that probability? Okay, so if you have that, we call that a joint density, because now we're talking about 2 different things. And this is and the probability, and we're going to assume itself that this x and y lies in a region D. Okay, so this is how you would find the probability itself. So it's basically a double integral, just the only thing that's different is that the integrand is now going to be a probability density function. All right, so all we really got to do is really draw the region, D or R, whatever you want to call it, integrate it out, and then just go ahead and do the problem. So suppose that x is the amount of time in minutes a fisher waits before catching his first fish, and y is the amount of time before another fisher waits before catching his first fish. then the joint density is given as this. And if you are interested, this is actually what we call the exponential distribution. In probability, we have a whole bunch exponential distribution. Okay. In probability and statistics, we have a whole bunch of different types of distributions that model different things and different phenomena. So exponential distribution is the time before this first event occurs. So in this case, we're looking at fish. But there's a whole bunch of different families of distributions. So this is a probability density function. So find the probability that it takes both fishers less than 2 minutes to catch their first fish. All right, so let's take a look at that. So we want to know that the sum of so we got fisher number 1, x here is the amount of time for fisher number 1. I'm going to call fisher number 1. And then y is also going to be the amount of time for first fish also. This is for fisher number 2. And what we want is together, I want both fishers to catch their fish in less than 2 minutes. So basically, what I want is that I want x plus y, the sum of these guys, to be less than 2 minutes. Okay, so whatever their sum of time it is to catch their first fish, it better be less than 2 minutes. Okay, so now what we're going to do is let's draw this region. Well, if we think about this region, let me go ahead and solve for x. We get y is less than negative x plus 2. So if we think about what that looks like, you can see that here's your x and here's your y. This is going to be a slope of, so up 2, and then we're going to go down 1 over 1, and then down 1 over 1. So this graph basically looks like this. This is the region that I'm looking at. Everything that's less than that, right? Okay, so we're looking for this rectangular region. Right, so this rectangular region, and this guy is basically y equals negative x plus 2. Okay, this actually should be dashed because we don't want it to be equal to. But really what we're looking for is this particular region. Given that the probability density function is this exponential. All right, so how do we find the probability? Okay, well, very easy. We want to find the probability that both fishers is less than 2. This is going to be over the double integral over the region of the function itself, the probability density function. So what would this be? Well, this is going to be the integral. So let's go ahead. This is going to be a type 1 integral. So this is going to be from 0 to negative x plus 2. And then from 0 to 2. The function, the density function is 2e to the negative 2x minus y. And then you're going to have dy dx. All right, so now let's go ahead and just solve this problem. One of the things that we can do here is do it this way. So we can take u. So we're going to let u be equal to negative 2x minus y. So when we take the derivative of this, right, we're going to pretend that negative 2x is a constant, so that's going to go to 0. Y, the derivative of negative y, is going to be negative 1. It's going to be with respect to y. So we're going to have negative du equals 1 dy. So when we take a look at this, this will be the integral from 0 to 2. Actually, let me pull out that 2. Integral from 0 to 2. Then integral from 0 to negative x plus 2. Remember that these guys belong for y. And then we're going to have e to the u. So we're going to set the whole thing equal to u. And then dy is going to be equal to negative du. And I'm going to put that negative on the outside. And this is going to be between... Oh. No. Okay, keep going. dx. Perfect. All right, so now we're going to have negative 2, integral from 0 to 2. Integral of the e to the u is just e to the u, so you're going to have e to the u, which is going to be negative 2x minus y from 0 to negative x plus 2 dx. So let's plug that in. Negative 2, integral from 0 to 2. Plug in the negative x, so I'm going to have e to the negative 2x minus negative x plus 2 minus e to the negative 2x dx, because the 0 is going to go away. So my first one, I'm going to have negative 2, integral from 0 to 2, e to the, so this was going to be a positive x, so that's going to give me a negative x, and that's going to be a negative 2, minus e to the negative 2 dx. And now I'm going to take the antiderivative of this, so we're going to get negative 2. This guy is just going to be negative e to the negative x minus 2. The other one's going to be positive 1/2 e to the negative 2x from 0 to 2. So you're going to get negative 2. Plug in the, this is going to be terrible. So negative 2 goes outside. I'm going to have negative e to the negative 2 minus 2 plus 1/2 e to the negative 2 times 2 minus, we're going to plug in the 0, negative e to the 0, so 0 minus 2 gives me negative 2, plus 1/2 e to the 0, which is basically 1. Alright, and all we really got to do is plug this in my calculator. I did this offline, but basically the answer is 0.747 or 8, sure. Alright, so basically what this means is that there is a 74.8% chance that both fishers will catch their first fish within or less than 2 minutes. Okay, so this is basically what it would be. And remember, time is positive. That's why we didn't go on the outside stuff. Now, before we're done, I do want to make this little brief note. We also do have one more type of application that we're not going to do, but I do have it here. This is miscellaneous, so we can do a charge of a plate. So suppose that the electrical charge is distributed over a region which has area R in the xy plane, and its charge density is defined by the function sigma xy. So this guy is equal to sigma sub x. This guy we call sigma, and this is what we call the charge density. So it's kind of the same thing as the mass density, but now we're calling this charge. So this will now represent a charge. So maybe there's electricity throughout an entire plate. So let's say you have this rectangular plate and there's electricity going on in here. So if you want to find the total charge Q of this plate, well, it's basically going to be exactly the same. So you kind of have a couple of things. So we know that mass is just basically the double integral over the region D of the mass density. We have probability is just equal to the double integral of the probability distribution, the joint probability distribution. And we also got the total charge is going to be equal to the double integral of the charge density. So we got 3 different applications for 3 different things for double integrals. Okay, so here Q is going to measure it in coulombs, where 1 coulomb is about 6.241 times 10 to the 18 protons. And then one last thing is that we do have a triple integral for the centers of mass formula and also moments of inertia. So here we don't have a thin plate. Here we have a some sort of solid. So maybe we have some sort of rectangular solid. And what we want to do is that kind of like the Ferris wheel that I was talking about. So maybe you have a Ferris wheel, and maybe you have this cube, and it has, each of them are patches of mass, right? So instead, my rho, which is my density, is mass over volume. So you can see why here we're taking the mass, taking the triple integral of of the density, multiplying it by its volume. So now mass is equal to rho times volume. So these do exist. This is absolutely horrific. I would never make you do something like this. It does exist. I don't know why, but typically what you would do in this case is that you would have some sort of computer software to just do this for you. At this point, that's where you have to go. This already doing a double integral with a thin plate with variable density is pretty tough. But these do exist, just so that you can take a look at them, take a wave at them. But they do exist. Also, the same can be expanded for charge and also for probability density functions. Okay, but obviously when we go into this realm, it gets a little bit more crazy. So that's basically some of the applications so that you guys can see where double integrals are also useful in.